Good morning, I'm Mr. Ish. Thank you for joining me for this video. We're looking at a single comprehensive evaluation of that integral that we see over there, 0 to pi secant x dx. It's a type 2 improper integral form that will come into play over here. A good way to start this question is to start with a good graph because it'll orient us to what we're doing here. Some of us may not need to graph it, but just for the purposes of video we might as well. We can always look at everything here with regards to 90-degree angles. That way we can have a good amount of symmetry with regards to our intervals, not being too distorted. Here's a cosine function right there. You know, when you do the reciprocal of the cosine at its x-intercepts, you get these vertical asymptotes, and the secant function can very well be developed along the cosine and these asymptotes that arise. We're looking here at 0 to pi, from 0 up to pi. You know, right here in the middle we have this infinite discontinuity at play. Going from the left towards this vertical asymptote, our secant function shoots up. Going from the right towards this vertical asymptote, our secant function shoots down towards minus infinity. Now it wouldn't hurt to actually eliminate the cosine function so we can have more clarity, and this is what we're looking at. When we're looking at from 0 to pi over here, you know our interval can be presented as such because 0 is very well in the domain of secant as well as pi. Just by looking at that, you'd never know that there's some discontinuity involved unless you are familiar with the graph. But what are we looking at here with regards to areas? For this top part, we're looking at an area below the curve, and it would look something like this, and you know it would shoot up over here along this asymptote. Well, this is the part below the curve, and this right here would be literally a part above the curve, and we're looking at here with regards to the shading, all of this, and then it's going to shoot down along here. We have to find the cumulative result of that area and what it can be. Very likely we will see divergence over here, but we have to mathematically show that to be the case. We're looking at from 0 to pi both in the domain, but when we split this up with regards to the asymptote we have, we're looking at 0 to pi over 2, and now we have that. And then we're looking here from pi over 2, and then we jump up to pi. And then we see how the brackets play over here. 0 and pi are included, but pi over 2's are not. And that helps us develop the limit form over here. We're looking at limit as t approaches pi over 2 initially from the left. We're looking at everything here from 0 to t, and then secant x dx. Then we have this cumulative effect. Remember the integrals in terms of their intervals, they add. Then we're looking here from limit t approaching this pi over 2, but we're going to be approaching it from the right. And then we'll have again here from t up to pi secant x dx. That all represents exactly the gist of this question. If we were to just erase this graph over here, because now we know and we understand what we're looking at, we can very well evaluate all of this now. Our expression over here looks good in terms of the limit applied to this improper integral. I believe we are in a very good position. We just have to do the antiderivative of that, and it's not hard. We know we have limit as t approaches this pi over 2. From the left we have the natural log secant x plus tan x coming into play, and you know this right here is the antiderivative of secant x integrand, and you're going to look at this from t to 0. Then we'll have this plus, and then we'll continue over here, limit as t approaches pi over 2 from the right. We'll again have the same antiderivative, secant x plus tan x, all the natural log of that from the interval t and then pi. You'll have to put the t and then the 0 here for the first part, the difference of the two, and then pi and then the t and the difference of the two. What we can do over here is create some space, because this is going to be a bit of a time consuming procedure, especially if we don't want to take shortcuts. We have all of this in our memory, so we can erase that. Very quickly demonstrate what we will look at in terms of our limits and how they'll play here with regards to the curves we're looking at. If this right here is my secant x, and this here will be my tan x. You know, we're looking here at a pi over 2, and then the curve for the secant x was going like this, and then it was coming like this. For the tan x, you know, we're looking at everything here from 0 to pi, right? The tan x would look something like this, and then we'll have a little bit coming from right here from the other interval. So we have all of that in play. Now what we have to do is the actual procedure right here. We're going to do natural log secant x tan x with the t in place, then the difference of that with the 0 in place, especially for those values coming here from the left. When we're coming here from the left, we have to focus on this part right here first, coming from the left, and we'll apply all of that. Let's do the upper limit first, the t. We're looking at secant pi over 2. When we're coming here from the left, secant is shooting up towards positive infinity, so we'll have that. and then tan pi over 2. When you know you're coming from 0 towards pi over 2, because this vertical asymptote is pi over 2, and you're coming from the left, your tan shoots up again towards positive infinity. And then we have to do the difference now with the zeros coming in place. Zeros are easy. Secant of 0 is a 1. Tan of 0 is a 0. So that is the first part right over here. All evaluated with regards to the upper and the lower limit, the difference of the two, but for the limit where t is approaching pi over 2 but from the left, we have to look at these from the leftward direction. Now we'll have this plus sign, we'll bring it here. Now for this part over here, let's evaluate this. We have to remember here the limit is coming to pi over 2 but from the right. We have to feed in the pi and then the t and then the difference of the two. Pi, secant of pi is easy. You'll have a -1 over here. That's fine because the absolute value will take care of that. Plus tan of pi is same thing as saying sine of 180 divided by cosine of 180, which is 0, right? Let's do the secant and the tan with the lower limit t. And remember here t is approaching pi over 2 from the right. When we're approaching based on the secant function towards this pi over 2 from the right, we're dipping down here towards minus infinity. We can have natural log here minus infinity. Plus tan is approaching this vertical asymptote from the right and it's going to dip down here towards minus infinity. So all that remains now is to actually evaluate this. In the first part we're looking here, we're getting a natural log of an infinity, and you know that's going to equal to an infinity. And natural log of an extremely large number is in infinity. Here we have natural log of a 1, which will 0 out. Here we have a natural log of a positive 1, that'll 0 out. Here we're looking at a minus natural log of a really large negative number in terms of infinity. Some may argue that here this will become a positive infinity. These two will cancel out because -0 plus 0 cancel out. Here you'll get a natural log of a positive infinity by means of the absolute value. Here you have a natural log of infinity, but by cancellation effect, all of this should technically equal to 0. Some may argue that might be the case. And if you were to look over here with regards to your area below the curve, secant x up to this pi over 2 and shooting up, and then area above the curve for this other part and then shooting along this, you could say that this area and this area by means of net effect should 0 out, because whatever you have on this side should equal to that in terms of positive and negative, and the net area here should be 0. But technically that type of reasoning is wrong. The reason why it's wrong is because of the general principle. When you're looking at a question like this, when part of an integral in terms of its interval, when part of that integral over that part of the interval diverges, then you might as well assume that it diverges over the entire interval. Meaning if it's diverging like from 0 to pi over 2, then you might as well assume that the entire question is divergent over the entire interval, and here our entire interval was 0 to pi, and you know that pi over 2 just happened to fall in between as a vertical asymptote. So even though one might argue that we are getting a net 0 here as an area by means of the cancellation effect, but that really is not the case. When part of your interval diverges, you might as well diverge the entire interval, the entire expression or the entire function diverges, and then your answer here truly would be divergent, or divergence is at play over here. And the reason why it is because you cannot evaluate some of these limits. Think about it. Limit as t approaches pi over 2 from the left, limit as t approaches pi over 2 from the right. Both of these left hand and right hand limits are not the same. From the left hand, as secant x approaches pi over 2, we're getting positive infinity. From the right hand, as secant curve approaches pi over 2, we're getting minus infinity. Right hand, left hand limits are not the same, so you definitely do not have a situation here where limits exist, because if the right hand, left hand limits are not equal to each other, limit does not exist. Moreover, if you're getting answers such as these, positive or minus infinity as limits, they're not true limit answers and not truly acceptable answers in terms of a limit. The answer to this question is divergence, that this integral, this question experiences divergence. Limits do not exist, and I wouldn't go with this answer of 0. I would go here with the answer of divergence, that this type 2 improper integral experiences divergence and the limits do not exist. With that, let's end this video, and I thank you for watching. Have a good day. Bye.